right, hello everyone. So we have this optimization problem which says find the largest rectangle that can be inscribed into a circle of radius 5. Okay, so it's a calculus question. And the first thing you want to do with these types of problems is, if you can, draw out the scenario. So in our case, I'm going to go ahead and draw a circle, radius 5, and we have to put in a rectangle inside of that circle, essentially. And it would look roughly maybe something like what I'm drawing now. And the word inscribe basically means that it's inside the rectangle and that the four corners touch it. Okay. The next thing I want to do is write the function that I'm trying to maximize or minimize, which would be what here? Well, we're looking for the largest rectangle, and we could say that is the largest area that we want to find. So we would have a width and a length, column X and Y here. However, our problem is that you have two variables, and we want to try to use our optimization techniques that we have from calculus, for which only one variable works out pretty nice here in this class in Calc 1. So we're going to build some kind of relationship between the variables. That's what we call the constraint. Now that constraint often comes from the picture that you see. And for this problem, notice how you can extend the radius out in the other direction, and you would get a diameter. Okay, and that diameter would be 5 plus 5, 10 feet total. Okay. Or 10, sorry, 10 units, I apologize. We don't have any units here. And if it's clear from the picture, you could use Pythagoras' theorem here, and you would have x squared plus y squared equals 10 squared over 100. That would be our constraint, because the variables are constrained by that equation. And from here, from knowing that constraint, I can go ahead and solve for y. As such, and I can replace the y in the function that we're trying to minimize or maximize. Sorry, in this case it's maximize, with that square root of 100 minus x squared. Now technically this is a plus or minus, but we're talking about length here, so we're not going to take a length to be negative. So now we have our function, and if possible, we'd like to go ahead and find its domain. Okay, so it's all the possible values that work out for the variables, and this depends on the physical constraints of the problem. So in our case, for example, if we look at we're going to be looking at the x's here. The smallest x could ever be is 0. Okay, not quite 0, because you'd have no rectangle. And the largest it could ever be would be what? Well, the largest x could be, I would say, is the diameter 10. Okay. All right, because at most, if you're looking at x is talking about this width. What's the largest the width could be? Well, technically, yeah, all the way up to 10 there. Okay. However, here's what we're going to do. We're going to include 0 and 10 in part of the answers. And I didn't include 10 before, sorry, because I had put a parentheses, because I can't have 10 technically, because you'd have no rectangle again. But now I am going to include them. You might say, why? Because we want to use something called the extreme value theorem, which says that you have a closed interval on a function that is continuous, which this function is, and I'll let you check that. Then you will have a maximum or minimum. Those usually will occur at the endpoints, or where the derivative is equal to 0 or undefined but continuous. So that's why we're making it a closed interval, so we can use that theorem. Okay. All right, so we're going to go ahead now. Once you get all that, you're going to take your derivative, and I already took it, and if I were you, I would stop this video and compute that yourself. You have to use the product rule here, and then when you take the derivative of the square root of 100 minus x squared. You have to use a chain rule. So next thing is I'm going to set a prime equal to 0. And if we move one thing over to the other side, and we cross multiply, sorry, that's pretty awful there writing. We would get 100 minus x squared times 100 minus x squared, square root on both, I'm sorry, equals x squared. So just multiplying these two right here together, and then these two. And this right here would turn into 100 minus x squared because the square roots cancel. This would be x squared. So 100 equals 2x squared. X squared is 50. Or x would equal square root of 50, which is 5 root 2. And again, I'm not considering the negatives here because of x is the length. So we got our point, and that's of interest. Now, technically, I need to look in for points where the derivative is undefined. But for which f of x is continuous, sorry, in this case it's a. And that technically would happen at 10. Right, and you look for points that are functions continuous, and I'm assuming, because of the interval was 0 to 10, I'm going to just for a second assume left continuity, okay? Meaning that when I say left continuity, I'm saying that the function's continuous at 10. And yeah, technically this is a critical point as well. However, it is not, I'm already making up for that when I have that closed interval, okay? So I'm going to now do the following. I'm going to go ahead and plug these points back into the original function and see which one gives me the maximum value. And that's always how this works out. You plug in any critical points and the endpoints of your closed interval into your function and see what you get as a maximum or minimum value, whatever the question is asking. If you plug 0 and 10, you get 0 for both. And if you plug 5 root 2, you would get 5 root 2 times 100 minus 5 root 2 squared. 5 root 2 squared is 25 times 2, so it's 50. So this comes out to be 5 root 2 times 5 root 2. So it's going to be 25 times 2, which is 50. So you're going to get the maximum area when you have a area of, sorry, when your length is 5 root 2, okay? Let me go back to the question here real quick. Find the largest, yeah, so that's what we're looking for, just for the actual area. Sometimes with these questions, they'll ask for the dimensions, meaning like how wide was it, how long was it? So we know it's 5 root 2 units long. And if that were the case, they were asking you how long and wide was it? Well, you can always just plug in your value that you found back into the constraint equation, or in this case, the constraint solved. So it'd be the square root of 100 minus 50, which is the square root of 50, which is 5 root 2. So your dimensions would be 5 root 2 units by 5 root 2 units, which would be a square, okay? Last but not least, when you're working on these problems, the hardest part typically is finding the constraint equation and the equation that you're maximizing here. The calculus isn't usually that bad, but I just wanted to make a point that if you're struggling with that, that can happen. That's not an issue, okay? And really, at the end of the day, it's perfectly normal. It takes some time, but once you get more practice with it, you kind of get the feel of what how this works. Okay, well, I appreciate your time. Hope this helps. Thank you.